first half, our first part, we'll basically look at RDF and OWL, or RDFs, which are basically the two semantic web standards for writing the base packs. You use RDF, and for writing the background knowledge, you use OWL. Okay, just it's an arbitrary distinction between these two, but really they're both logic. You know, they're just syntax for providing for writing logical statements, first order logic statements. Okay, actually a subset of first order logic statements. So that's what I am planning to do. Before I go forward, are there any questions? Okay. So again, this is just a summary of what we discussed last time. So XML provides a way to capture the syntax of a file. I mean, XML schema provides a way to capture the syntax of a file, valid syntax of a file. XML provides a way to give that syntax, the tag structure and so on. And if you want to provide, so semantics come essentially from, in terms of, and I cannot actually go into how formal languages have semantics. I mean, you should have taken some other course, like Intro to AI or something. But in general, semantics come from, you'd say the meaning of a sentence is the set of words where that sentence is true. That's the meaning. Okay? And the meaning of another sentence is the set of words that is true. And the conjunction of meanings of two sentences is the intersection of these words. Okay? And if you say that there is a sentence which has no meaning, that means essentially there's no word where it is true. No possible word where it is true. That's the approximate idea. And in trying to provide semantics for any language, any logic, you first start talking about what sort of words are you talking about. In the case of propositional logic, which is sort of the simplest logic, where you write things like PRQ, P implies Q, and not P, those kinds of statements. In general, the words there turn out to be basically interpretations over proposition symbols. So that basically means a particular word would be, say, P equal to true, Q equal to true, and R equal to false. That's a word. Okay, so if you have n propositions, then there are 2 power n possible words. And given a sentence, the meaning of that sentence is the subset of these 2 power n possible words where that sentence evaluates to true. And all Boolean logic provides you is a way of figuring out, given a sentence, you can evaluate it in a word and see whether or not it's true. Okay, so that's where essentially semantics come from. So syntax doesn't directly give you the semantics. You need to talk about the words. And also the other issue is the meaning comes from connections between proposition symbols, the predicate symbols. Okay. So essentially, we, in the previous example, we looked at the fact that we need a way to specify base facts, and base facts are just binary relations. Binary means it's a relation over 2 things. To some extent, this RDF, this stuff really can be thought of as just essentially equivalent to relational databases. Okay, I think I mentioned this last class. If you have a relation, in relational databases, each table corresponds to a relation, right? So you have column 1, column 2, column 3, so maybe these are attributes. Attribute 1, attribute 2, attribute 3, attribute 4, and then there are some values, V1, V2, V3, V4. Okay, that's a single record in this table. Now, you can essentially talk about a tuple ID here, T1, and then start writing RDF statement saying the T1, A1, B1, E1, A2, B2, E1, A3, B3, and so on. These are the triples, right? So you just basically can easily compile a table into a set of RDF triples. Okay, pretty much the only difference is in the case of a table, on the top you write the columns names, and then essentially the tuple itself doesn't have the structure. In the case of RDF statements, you are essentially saying the tuple T1 has its A1 value B1, its A2 value B2, and so on. What that also means is that RDF is, if you have a bunch of RDF triples, you can do normal SQL style database query processing, right? So for example, in fact, so the question then will be that you need an SQL that works on RDF, and we will talk about a particular query language called SPARQL, SPARQL, which basically does that. And it will allow things like joins over triples and so on. Okay. The next thing, of course, is to provide the background, to provide the relations between A1, A2, A3, A4, and maybe other attributes. So for example, it may be the case that A11 is the same as A1. Or the value of A11 will be true whenever A1 equal to V1 and A2 equal to V2. So those are all background knowledge statements. Okay. In the context of databases, for example, can you think of, I'm assuming some of you, how many of you have done a database course? Okay, so you've done, a lot of you have done database courses. So what can you think of background knowledge in databases? So you have tables, you have schema, what else is there? Tell me some background knowledge in databases. What? Yeah, I mean, that can be anything. So tell me something else. What? What? Constraints, functional dependencies. These are all background knowledge. Do you see what I'm saying? So there are ways of actually, there is background knowledge on top of normal relational databases too. And typically you use them, in fact, you use the functional dependencies to normalize databases. If you remember the way databases are normalized. You have a universal table and you split it into multiple small tables so that the Cartesian product over those small tables gives you back the universal tuples. Okay, so there is background knowledge there. It's just that there is no agreed upon syntax for them. Every vendor has their own background knowledge. And furthermore, there will be certain types of background knowledge is allowed. You can't normally say things like, if A1 equal to V1 and A2 equal to V2, then A3 will always be true. Or if A1 is greater than A2, then A3 will be true. Those are arbitrary statements about how properties of an entity may be correlated with each other. Okay? And you get to say that, when you are talking about background knowledge, that's what you're doing. In database community, actually, before the advent of Semantic Web, you have the RDBMS, and there were deductive databases, which sort of have disappeared right now, but have come back in a different form, essentially. A deductive database is a database of tables plus some additional background knowledge. That's what it is. Okay? And so, in some sense, RDF plus background knowledge is sort of reinventing deductive databases. Okay, by a separate set of people. It turns out somehow Semantic Web stuff doesn't get published in database conferences. It gets published in different sets of conferences. Okay, but the connection is the same idea. And then you're sort of agreeing upon an exchangeable standard. As long as all of us write our background knowledge in this particular syntax, then presumably we can exchange it and read each other's background knowledge. Okay. So those are the things. So we have the two parts. One is syntax for RDF and the syntax for the background knowledge. Clearly, the syntax for background knowledge is going to be more hairy than syntax for RDF, because RDF is just triples. It's just subject, property, object. Okay? So it's like the simplest kind of syntax. Okay? So we'll look at that first, and then the RDF schema and all. In fact, before, right now the standard for background knowledge is, I believe, called OWL, and there are variants of OWL. Just before OWL, it used to be called RDF Schema, which is actually a bad name, because you would think if RDF Schema would be to RDF what XML Schema is to XML, except it's not quite true. Okay, one is providing background knowledge, and one is providing, I mean, you know, it's a very interesting question. I'll show that to you again when we're discussing this. It's worth thinking of, is background knowledge over RDF triples the same as a schema syntax for an XML file? Okay, so that the term was not a particularly good term, and in fact they also extended the expressiveness, and they're using OWL, which is still not first order logic. It is a fragment of first order logic called description logics, whereas as mentioned last time, description logics basically talk about relations between sets and subsets. That's what they try to do. And one advantage is for large parts of description logic, large fragments of description logic, worst case inference is still tractable, which is not true for normal first order logic. Worst case inference is semi-decidable. Okay, so that's basically, so I'm allowing you to say some things in the back, but only if you can write it in my language. If you can't write it in my language, you can't say it. And I'm making the language simple enough that if you only write it in that language, then the reasoning I have to do would be constrained. You know, I don't have to do more than a polynomial amount of work. Okay, but that's actually an interesting point. I'll again talk about that too. You know, is it better to let people say what they want to say, and then you reason how much you can reason, or should you say that don't tell me more than I can reason with? This is actually a very good philosophical issue. This is true also of classes. You know, students would like teachers to teach them. There are two ways of teaching classes. One is I only teach you, or you want me to teach you only stuff that you can understand and do well on in the exam, so that you can feel good at the end of the semester, that all of us got A's, okay, whether you actually learned the subject or not. The other is I teach everything that is supposed to be taught in the subject, and then you will be getting 60s and 40s out of 100s, okay, which is better. And obviously, you know, if you're into GPS, clearly, you know, I think you'll be much better off just saying, you know, somehow make the subject be what we can understand, not what the subject is supposed to be. Okay, this is how dilution starts in teaching, but it can also be the way dilution starts in telling databases what you want to tell, the knowledge bases what you want to tell, because they're, you know, you are not allowed to speak more than 2 sentences, or you're only allowed to speak these kinds of sentences. Okay, that's an interesting debate in knowledge representation community. Semantic Web guys essentially say, we'll only allow you to say stuff in a particular format such that we can be sure that the worst case complexity of reasoning over that is going to be polynomial. Now, in some sense, database guys did that before already. They said, we'll only allow you to not give us any background knowledge. All background knowledge you can give us is RDF triples. Okay? And if somehow you think their background knowledge is important, somehow find a way of writing it in a larger database. Maybe replicate the data, maybe duplicate pieces of information. So that we can then say that the reasoning on the database is still polynomial in the size of the database. Whereas what you really would like to have done is, here's a little bit of data, and here is one nice universally quantified axiom. Right? And then basically, it would no longer be, the reasoning would no longer be in the size of the input, not be linear in the size of the input. Anyway, so that's the background on the RDF and RDF schema, the background knowledge on RDF schema. This stuff, I'm just going to go through it quickly. Again, if you really want to write RDF triples, the good thing is there is a well-understood syntax. Just as if you have to write a C program, there is a well-understood syntax. Every C program compiler will understand the correctly written C syntax. And you better understand that and you write it. But teaching syntax here is pretty boring. Okay, so you just have to, you know, go pick it up. So I will show you that there is a syntax and how it sort of looks like, but you know, my interest is not to give you the entire syntax manual. Okay, So you have subject, predicate, object triples, basically with the binary predicates. So here in this case, Ian has a colleague, Uli, and this is basically what you have. It's sort of you can think of a graphical representation here between entities. Relations are the edges and entities are the vertices, right? And then you have to convert this into some serial language so that you can send it on the wire. And XML serialization is one. There are other serializations actually. I believe there is some 2 other names. I forgot. I mean that there are subsets of people who also agree on different standardization for XML for the RDF statements. But XML standardization is the most standard one. And so it's basically you will provide an XML syntax for writing this. I'll show that to you in the next slide. And then the other thing is each of these things really are essentially URLs in the context of web. So an RDF is a triple over 3 URLs. Okay, where this is a URL for an entity, this is a URL for the relationship, this is a URL for another entity. Okay, and then so actually they call them URIs, Uniform Resource Identifier, and a particular type of URI is URL. And on the web mostly use URLs. Okay. Okay. So here we are going to look at Ian has colleague Uli. So this is how this is particular XML serialization. So it looks reasonable enough. It says description about is this particular URL, and has colleague is the property, and notice that each property is a directed property. This is kind of a funny thing that RDF does. Each property is sort of directed. There's a subject, object for each property, and then has colleague Uli, and then so that's why the property of this URL called has colleague is the value this. That's what you're saying. Okay, and then you can write more descriptions. Okay, a store of RDF triples is a whole bunch of triples like this. That's all. Okay, this is basically your syntactic version of this. Now here's my so essentially RDF has an XML syntax. You agree, right? It's an XML syntax. Every description element describes a resource. Every attribute is nested element inside a description and is a property, and the property basically, again, after the property comes the URI. Okay. Resources are referred to using URIs. Okay. So the next question is that, in fact, this is an alphabet soup of standards. There is XML, there is XML schema, there is RDF, and we are about to talk about RDF schema. But RDF syntactically is XML, right? So would you think there should be an XML schema file for RDF files? This is something that you want to think about. Yes, because a well-written RDF triple should only have these things and nothing more. Do you see what I'm saying? So there will be an XML schema file, and all RDF files will have a link to their own XML schema file. So that's how XML and RDF are connected. RDF is a particular subsyntax of XML. Okay? And you're only allowed to write these kinds of sentences. Not every arbitrary XML statement is an RDF statement. And since you're only saying certain statements, certain XML statements can be written, you better write the syntax of your file. So it's the store of triples of the following form. You need to write the XML schema for that. That's what is done. So that's a useful thing to keep in mind. There's an XML schema for RDF files. In fact, there'll be an XML schema for OWL files too. Okay, that's basically a syntax standard. That's just a syntax standard. Okay, so you can have multiple triples, and if you keep having more triples, then in essence, you have a bigger and bigger directed graph. Okay, so the question then, so basically in this case, the subject of one statement can be the object of another statement, and you essentially have, you can think of this kind of a graph as a linked data, where the links are the relations. So these are kind of, they're not pages, they are entities, and these are typed links between them. Okay, so this is why just a store of RDF triples is also called a linked data. And then there is a whole bunch of people working just on linked data, which is basically doing databases, normal databases on RDF triples. Okay. Okay. Now, the other thing, of course, is an RDF basically, you don't have any background knowledge. You're just saying there's an entity name, there's a property name, there's another entity name, that's it. And you don't say, for example, that if Ian has a colleague, Uli, does it necessarily mean that Uli has a colleague Ian? You all probably think colleagueness is transitive. I mean, colleagueness is symmetric, right? It's not a question of does Ian, it could well be that Ian likes Uli, Uli doesn't like Ian, but colleague is just, they both work in the same place. So if Ian and Uli are working in the same place, then it must be the case that both of them, it should be in the opposite direction too. Currently, the way I gave it, you won't be able to infer that. Right? To be able to say that, either you have to also put one more link saying Uli has a colleague Ian, or if you have, in which case you're kind of repeating obvious stuff, or you will have to, write the background knowledge. You have to say, for all xy has colleague, xy implies has colleague by x. That's one particular background knowledge. Right? That's what you should be able to do, and that's the kind of thing that gets done in the OWL part. Okay. So if you just go with the RDF, and as I said also, this can be thought of as linked data. There is, you can think of whether or not binary properties, the fact that RDF only supports binary properties is a big issue. I mentioned that that's not a big issue because in essence, you can, here it's a n-ary property, a table, a tuple in a database is an n-ary relation, right? But an n-ary relation can always be split into a set of binary relations. It cannot be split into a small set of unary relations. Okay, because the blow up here is instead of having one tuple here, you have basically, if there are k attributes, you have k triples. It's just a linear blow up. Okay? Whereas if you start allowing unary properties, then you will actually have exponential blow up. Okay, so this is considered not a huge problem to be able to just talk about binary variables. This is done in lots of places actually. If you do, in constraint satisfaction problems, for example, people just study binary CSPs because they have everything that n-ary CSPs will have, because an n-ary CSP, n-ary constraint can be written as a set of binary constraints without particularly blowing up the size of the database. In satisfiability problems, that is, a satisfiability problem is one where if you have propositions like this and you want to say this is a class and here is another class, here is another class. Actually, the CNF classes could be of the form P, Q, R, P, not Q, J, things like that. And what that means is this class is satisfied if any one of these is true. Okay? And if you have, normally a class can be very, can be arbitrarily long. You can say P, not Q, J, not M, W. Okay. It turns out that Boolean satisfiability is known to be NP complete. How many of you know this, by the way? Okay. Boolean satisfiability is like the canonical problem of computer science, and it turns out to be NP complete because, remember, the question here is I give you a whole bunch of constraints like this, and I'm asking you, is there a word which satisfies all the constraints? That means, can you give me true, false values to all the variables such that every constraint is satisfied? That's called Boolean satisfiability problem. It's a canonical problem. Everything, many things can be compiled down to that. Okay? It turns out general Boolean constraint satisfiability problem is NP hard. It's actually NP complete. That's the first one that was shown to be that. Now if I put a strong restriction on the size of the classes, and I say each class is one length, each class can only be length 1. The length here is 1, 2, 3 here. So if I tell you each class can only be length 1, how hard is Boolean satisfiability problem?
P.
What?
P.
P meaning what?
What?
What is
polynomial?
Polynomial, okay. Do you guys even realize that if each class is length 1, I already told you what the answer is. Do you see what I'm saying? So I'm saying P must be true. If I say one class is P, that means in the final solution P must be true. Another class is not J, that means in the final solution J must be false. I'm already giving you the answer. So the rest don't matter. So one SAT is extremely easy to solve. Okay, if you don't understand that, you're in big trouble. 2 SAT turns out also to be polynomial. That's sort of more tricky to understand, but 2 SAT also is polynomial. 3 SAT is NP-complete. From 3 onwards, every SAT is NP-complete. Okay, again, my point I'm trying to make is a 3 SAT is like a binary relation. It's a triple. And if you have a normal, general, Boolean satisfiability problem, you can compile it down into a 3 SAT problem with only a polynomial increase in size. Because of which it's possible for both this and this to be NP-complete. Whereas you cannot compile a general Boolean satisfiability into a 2 SAT without exponential increase, which is why 2 SAT can be polynomial while general Boolean satisfiability can be. This is all about expressiveness. Okay, so my point is, when you took a triple as the basis for RDF, you didn't lose anything from the point of view of worst case expressiveness. Okay. Okay, so this is just the base facts, and there's a lot of interest in just these base facts currently in Semantic Web. Even though OWL is something else that we'll be talking about in a minute, most of the current action in Semantic Web community seems to be just generating huge RDF triple stores and doing databases on them. But doing normal querying on them. And querying on just RDF without background knowledge is isomorphic to querying on databases. You should see this, right? Because I just wrote the table in terms of triples. Okay? So there are people who are, the only difference is that all the triples are self-describing. They give the property, the tuple name, the property, the value. The tuple name, the property, the value. They are basically self-describing. Okay? And so there is, a lot of people trying to write down general publicly available data in this RDF format are getting people to agree to put their data out in RDF format. Okay? There is a digital government initiative where basically a bunch of people convince the government that you guys have data and you always follow rules. Why don't you follow our rules? Just write all the data in RDF, or at least give us access to your database. We can trivially convert it into RDF store. Okay, and so these are basically a whole bunch of data sets that are available on the web. They're all in RDF form, and you notice that in the middle of it is Dbpedia. Dbpedia essentially is a data set which takes the info boxes from the Wikipedia, which is the structured part of the Wikipedia, okay, and basically converts it into RDF. So actually Dbpedia is not waiting for somebody to give it structured data, it's doing extraction. So that is the second part of today's class, where you directly extract information. It turns out that when you're extracting information, extracting it from here is hard. Extracting structured information from this text is hard. You can do it, but unless you know full NLP, you can't do this. The machine can't do this. But extracting stuff from text, from table is very easy, right? Written in must be a property, and the other side must be the value, and the license must be the property, and this must be the value. So in fact, the info boxes are really already RDF triples. It's just they're put in a human readable form. And what Dbpedia does is essentially it converts them all into RDF triples and then provides access to it to people. you can go there and play with it. Okay, and this is basically the way, I don't know if you can see this, but it has, it basically says it has a local copy of the Wikipedia, and it does some extraction of the triples from the wiki, from the info boxes and stores them. Okay, so the raw data is available for people right now. Notice that if one info box is written in and says Scala, Java, and ESP, other info box says coded in and says Lisp and Java. Okay, then there will be two RDF triples, one called written in Java and other called coded in Java. And you probably think they're both the same, right? But obviously, when I just convert it into RDF triples, I don't get that, essentially. So somebody else has to still, the background knowledge has to be still supplied. Currently, all Dbpedia does is just provide you the RDF triples. So in a way, it's just database, large-scale databases in RDF. Okay, and so if you want, and then it also allows front ends on those databases to query. One particular standard for querying RDF triples is SPARQL, which is sort of like SQL. And so, for example, in this case, suppose I have a whole bunch of triples which are telling me about capitals of countries and countries themselves. Okay, and so this particular query, which has its own syntax, it's saying select the capital and the country, okay, where it turns out that you have one triple which starts with X, city name, capital. I don't really care about X, okay? Somebody is, basically there is some triple in your database where blah, 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 city name, and capital. And then you pick this capital up, okay? And then, so that basically whatever you're giving as capital should be a city, and it should be capital of something. And that something must be a country. This is your normal join query in SQL. Right? Okay, I just wrote it in SPARQL. Okay, so if anybody asks you, do you know RDF? Say you know, because you know databases, and basically that's what it is. You are just writing it in triple form. Okay, it's just a separate syntactically different form. Except now that it's in RDF form, it's easy to write background knowledge. There is also agreed upon standard for writing background knowledge, if you want to write it. Yes? So,
about IBM machine and what they did they do something similar to this? Or?
Which one? The Watson?
Yes.
No, Watson is a completely different issue. I mean, basically they may have databases, structured databases, okay, and they may also do extraction from normal text, which is the second part that I'll be talking about. Okay, so the idea is we are in a transition period, understand that. I mean, we'll always be in a transition period with respect to something or other, but we are currently certainly in a transition period with respect to structure of data. Okay, either one or two of one of the things, there is, so we basically have a lot of unstructured data, and so you may have to actually extract structure from it, but there's also a lot of structured data. So it should be, so there are people interested in giving you structure. That's when they give you these databases. So these can be written down into RDF. Okay, and if I have text, I can extract the structure and write it into RDF. That's what is information extraction. Okay, Watson does a mix of all of these. Okay, because there are some structured databases already on the web. In fact, government data is a classic case in point. The digital government initiative, most of the government agencies have huge databases on you. Okay, and thankfully the only good thing, you don't have to particularly worry about your privacy because their databases don't talk to each other. So even if it's doing crazy bad things, they probably will never figure out because this database has different column titles and this database has different column titles. Okay, and you'll never know. That's how we let lots of things happen. So from the government point of view, in fact, by the way, the interesting thing is that you must have heard about this with respect to this class. The connection with 9/11 is that one of the big recommendations from the 9/11 Commission is that government databases should talk to each other. Basically, there was enough information sitting in different databases about the fact that certain people went to flight school, certain people were doing this, certain people were doing that. It's just that they were not connecting. And it's not just connection in terms of people connecting it, it's also because there is no automated support. Because they all are structured, so they are all in RDF, and that still doesn't mean a thing. If in fact, you have different property names for the same property, or you are not writing knowledge about the correlations between properties. Okay? So in fact, information integration, alignment of data, I mean, they didn't say information integration, but alignment of data is something that shows up in the thick 9/11 Commission report. Okay. Okay. So that's basically for doing querying over RDF. So next thing we want to talk about is how to write. Why do you need background knowledge? I assume you already understand that you need background knowledge. RDF gives the base tuples, and RDF schema are all give you a way of writing the background knowledge in this, axioms, logical axioms. Okay, and as I said, RDF schema to RDF is quite different from XML schema to XML. One is background knowledge. I mean, it's interesting to think about. I won't write a couple of sentences, but think about that contrast. So here is a picture to give you a feel for what background knowledge does. That's what I tried to do in Ramayana example, but you can get in that attempt. So if I have discrete mathematics, is taught by David Billington. That's an RDF triple. Okay, the course discrete mathematics is taught by David Billington. If you read this, you already understood this, because somehow you bring to bear the context and you think, oh, discrete mathematics looks like a course. Is taught by, especially since there is a is taught by, it must be a course. And this looks like a person's name. This doesn't look like a course name. This doesn't look like a person name, right? And so you already have some background knowledge about what is taught by relation is supposed to be. And so you brought all of that to bear on this, right? But the machine, your database has no clue. For it is just X, Y, Z. X has the property Y, whose value is C. That's all it knows. Okay. If you want it to do more interesting reasoning, and remember the very beginning of the semester when I mentioned semantic web and background knowledge, the example I gave is Magellan went around the world 3 times. On one of his trips he died. Which trip did he die? Okay. All of you know the answer, but where in what I said is the answer? There's a humongous amount of background knowledge. And in fact, one of the more interesting questions from the AI point of view is how exactly is that background knowledge represented? Do you have a piece of knowledge sitting in your head saying, whenever Magellan makes 3 trips, he dies on the last trip? Okay, that's one, and that will allow me to answer this question. Whenever people make trips, whenever people make 3 trips, then they die. If they die on the last trip. That's more general, but still not general enough.
Are alive when they make trips.
Yeah, that's another thing. So that's one thing. A reasonable thing is to be able to do a trip, you must be considered alive. Okay, but you can also say that there are animate actions. Trip is an animate action, and you can't do animate action unless you're alive, which is even more general. As to what level of generality you have this knowledge in is a very interesting question. You don't write general knowledge just to solve the current problem. You have layers of generality. Okay. In 471, my favorite problem is for people to write down first-order logical axioms that will allow them to actually use a theorem prover to prove that if this guy died, he must have died on the 3rd trip. And the easiest thing that people will write is if you make 3 trips, you die on the 3rd trip. And that will answer this question, but then you'll start having all sorts of other questions. There is no traveling salespersons because, after 3rd trip they die. Right? So if you are not careful in writing your background knowledge, you can get into all sorts of troubles. Because you don't write background knowledge just for one problem. This knowledge stays with you and it's going to bias the way you're solving other problems. Okay? Anyway, so in this case, basically there's a huge background knowledge behind it. So discrete mathematics is a type of a course, right? And a course involves somebody teaching it, somebody, the name of the course, and it basically, and the person who is teaching it must be an academic staff member. Okay, and academic staff members, professor is an academic staff member, associate professor is one, and assistant professor is one. And it turns out David Billington apparently is an associate professor. So clearly he's okay, he can teach this course according to his background knowledge. And then he starts by his being represented here. Okay, and then academic staff member, if you have just this, you may be able to say a couple of things about this data, but this is a much bigger piece of background knowledge. For example, academic staff member is a staff member, and a staff member is a human. Humans, after a while die. So if you're hoping for this course, but not taught by David Billington, you can wait. One of these days, these guys won't be there, this guy won't be there, and you can get that course. Right? All these things you can decide because you have the same big background knowledge. Okay? And so writing this is what OWL or RDF schema does for you. So this is essentially, I wrote it in the graphical form, but it's just a bunch of logical sentences. And writing those is what you get to do in RDF schema. Okay. And it turns out that RDF schema is the first standard for background knowledge, which is a small fragment of logic, and then they extended it a little bit, and they currently use OWL, which is sort of subsumes to some extent RDF, and OWL itself, this is how the syntax of OWL looks. Again, OWL is an XML file. So there is an OWL XML schema. Okay, I mean, for you to be able to understand this series of lectures, you should be able to understand that background knowledge is constraining what worlds these facts can be true in. Okay, XML schema is constraining what is a valid RDF file and what is a valid RDFS file. Okay, and that's just, it only cares about the syntax. Okay. Anyway, so this is how this is mostly to show that OWL can be written in some XML syntax, and you obviously need to read the syntax manual, and then which will tell you if you are trying to write this kind of a logical sentence, this is how you write it in the OWL schema. Okay, and mostly the conceptual view you should have is basically these are all, notice that these are all class subclass relations. Like for example, professor is a subclass of academic staff member. Billington is an instance of associate professor class. And so in general, the kind of knowledge that's allowed typically in the background theory is class subclass relations. But normal first order logic is more expressive than that. There is knowledge that's more than just class subclass relations. And that should get to skip. Okay? So all language basically itself has variants, and a particular form called RDL corresponds to the description logic fragment of first order logic. And it has semantics equal to the description logic fragment of first order. Okay. And of course, so for the description logic, inference is efficient. It's not semi-decidable, thankfully. And so there are people who have written inference algorithms which will eat all statements and RDF triples and do theorem proving. Okay, theorem proving is logic's word for inference. Okay, so you give is this statement true given what you know? And that's, are you trying to prove or disprove that statement? Okay, so there are inference algorithms, but clearly, as of now, there's a lot more work that's been done in terms of getting RDF triples together than writing all universally agreed upon background knowledge yet. Okay, because it's not too obvious, as I was trying to get you to think about Magellan example, exactly what is the right level you want to represent this knowledge. It's not at all obvious, it's like the temptation is to represent it just the level of generality so that you can solve this problem. But then there will be one more problem, and then you'll get one more variation of this same piece of knowledge. And all of a sudden you have like a mess of knowledge axioms. So it's not very obvious as to how to write at the right level of abstraction. Okay. So in fact, much before Semantic Web, there used to be when basically AI folks were always interested in inference over logical databases. And there was a time when essentially people were happy enough that, okay, we'll do theorem proving on logical databases. All we need is somebody to write down all general knowledge about the world in a logical form once and for all. And the advantage of people writing this knowledge is you know it, but I don't know how to grab your brain. So we do this inefficient thing wherein I act like I'm teaching you, you act like you're either listening to or in some cases sleeping or checking cell phones. Okay? And then hope that some sort of transfer occurs. Okay? If I were to write all of this in if you are like a database engine and I have all this data already written once, I just open your head, pour it. And that will be 100% transfer. Only one person has to write down general knowledge about the universe. And then once that is written, then every computer can use it. They don't have to learn it again. This is a beauty. It's a great idea. You don't need to learn everything from scratch. Human civilization progressed that way. We didn't have to learn everything. Every generation had to figure out fresh from start that no, sun is not revolving around the earth. Then we won't go anywhere. Okay? But we have ways in which somebody writes it down, we read it. And so for machine readable form, if you can write in a machine readable form all the logical background knowledge once, then every machine can use it. And back in 84, 85 time frame, there used to be a project called Cyc, by a guy called Doug Leonard. And Cyc is for encyclopedia, the Cyc, encyclopedia part of it. And what he basically did is, he was doing quite well in research, so he convinced people that just, I'll build the entire universal background knowledge of humans. Okay? Not very specialized knowledge. I understand that there may be more about computer sciences, more about biology, but stuff like, if there are 3 trips and Magellan died on one of them, which one did he die? You did not have to go to computer science school or art school to figure this out. We all know this. In some sense, common sense knowledge is what a 4-year-old knows already. Okay, but the 4-year-old knows a humongous amount of knowledge about how the world develops, how the world operates. But they learn it. In the first 4 years, they have no school, nothing. This is what they do. They learn this stuff. Okay, if I can somehow write this down once, this is what Doug Leonard was thinking. Then people can just use this. Essentially. And so he actually did this project for a while and it was a spectacular failure. And it's a failure not because he was not smart, but because of the point I was making earlier. It's not at all obvious what is the right level of generality to write knowledge in. And furthermore, another very interesting point is common sense knowledge is highly defeasible. That basically means that every rule has an exception, every exception has a rule, every rule has an exception. Right? So the classic example is if I tell you that Tweety is a bird, you think Tweety will fly. If I tell you that Tweety is a cartoon bird, you don't know. And maybe you'll still say it will fly. Then I say Tweety just had an accident, you'll think it won't fly. Then Tweety is a magical bird, they don't have accident, they still may be flying. Okay, so you keep changing, whether or not Tweety flies as I keep giving you more information. Okay, in logic, in first order logic, as you learn more stuff, the theorem you prove never becomes incorrect again. That's the beauty of first order logic. So if you ever proved a theorem in your second grade, you can frame it and keep it, because even as you go through PhD, you will still never learn anything which will unprove that theorem. If in fact all that matters is first order logic. So that's why first order logic is called monotonic. Okay, it turns out real world knowledge is not monotonic, it's diffusive. And so in fact, Doug Leonard, one of the reasons Doug Leonard failed is because he was looking for normal first order logic representations for knowledge. And so first, he didn't know what's the right level of generality to write it in. And second, he had to allow this, plausible reasoning, plausible knowledge. And that's the second problem. Now, notice that so many years later, now we're talking about OWL. OWL is not even full first order logic. It's a subset of first order logic. And it does not allow defeasible reasoning. Okay, so we are not basically doing the entire world's background knowledge. We might be writing a little bit of extra background knowledge for some particular domain or particular class of domains, and that might help better reasoning over the knowledge, the data you have. Okay, so that's basically, in some sense, functional dependencies is a kind of background knowledge in databases, as I mentioned. And this stuff is definitely better than functional dependencies because this will allow you to set functional dependencies and much more. Okay. So this stuff, basically, this slide is about this point I already made, which is, should I stop people from writing what they know in the knowledge? So if they have background knowledge that cannot be written in OWL because it's not full first order, right? Should we then basically make them cut down their knowledge into a form that can be written in OWL, just so that you can say, I'm doing fast inference? Or should you allow people to write it in full first order logic and just say, I'm only able to do efficient inference on a fragment of what you just told me? What does IR do, by the way? What does IR do? Apart from the people who are actually sleeping, there are also people who are awake but are asleep in the class today. I don't know what to say. What does IR do? In this spectrum of letting, either say only the stuff on which I can do efficient reasoning, versus say whatever you want, but I'll do whatever I can. Where is IR? Yes?
Give me whatever you want.
Exactly. And that's a classic example. IR basically could care less. You can write Shakespearean sonnets and it will still look for keywords in it. It's not saying, because I'm doing keywords, please write only keywords. It doesn't say it. It lets you write everything, and as soon as you turn, it converts into a big bag and carries it home. Right? And in some sense, people feel better because they don't have to do anything special to do IR. They only are unhappy that IR isn't giving better information. Okay? At least on one side, the input side, they are not unhappy. They didn't have to do anything special. On the output side, they are perpetually unhappy. And when you are restricting the syntax in which the background knowledge can be given, for example, then people are unhappy both on the input side because I know something more and you're not letting me give it. And I'll always be unhappy on the output side because I forgot to write this very obvious thing and I would have thought you would have understood that. And you didn't give me correct answer. You see what I'm saying? So this is basically general knowledge. The issue of whether we should write, whether these background knowledge schemas should support any general knowledge, should they already put syntactic restrictions? That's the issue. And you know where IR falls and you know where Semantic Web falls. And what's interesting is you came to Semantic Web to somehow make better querying possible. And it is true. You can give answers to questions, with this architecture that you could never give with IR architecture. But then more people can be unhappy with this because they feel, I wanted to write stuff in my own, in the full format. Okay, so that's a very interesting, controversial issue. I think Semantic Web community right now assumes that we'll put the restriction on the syntax levels. So that's actually. Okay, this is actually the sentence, the entire slide that just captures what I just said. I'm not going to read it. Okay. So one last thing is, if you do have OWL standard, a simple thing you can do is this. Suppose you have two databases. Here is database 1, here is database 2. Notice that databases can be written in RDF, because RDF is isomorphic to databases. Right? So this is a store, online store, this is an online store. It has its own RDF format, and this has its own proprietary format. And the interesting thing is their columns might be different. Okay? Sometimes the columns are just renaming. That means somebody calls it writer, somebody calls it author. Other times the columns might actually be giving different kinds of information. A classic example is I might have one database which gives me salary of every employee. Another database which gives me the total number of employees and their average salary. If my query is how much does this company spend on salaries and how much does this company spend on salaries, I should be able to answer in both cases, right? But it won't be obvious because you normally write a query which only makes sense for either that format or this format. Or you have to write two different queries. You understand? That's what you do right now. You write a query for each of the databases. And so what happens basically is this problem with structure is there is just an explosion of schemas. If you have multiple databases, every database has a different schema. And so saying I have structured data might actually not be such a great thing because you may as well just throw away the structure because every column is differently named by different people and everybody has written a different way of schematizing the data. It's not even just a renaming. Now, if you have a situation like this, and this is a big problem in all corporations, all enterprises, all companies. These are not people who are writing stuff in English. They actually have databases. Except they'll have 3 databases that don't talk to each other. Okay, as I already told you, government has this problem. Now, NSF, National Science Foundation, is a premier research organization that funds research in US. Okay, and National Science Foundation now spends a lot of money on information integration and extraction, which are these areas that we're talking about. The issue that they gave as a whenever they are trying to start a new big initiative, they have to go to their bosses and say, we want to put money into this research. And they'll ask why. What good is it going to do to common public, right? Common people are very unhappy in general because there's research being done which never really is useful right now. And 20 years from now, I may not be alive. And why do I want to pay for it right now? And so how do you make an argument to your boss as to why this is useful? And one example that one of the program managers told me once is they just wanted to find out how much money has NSF given to historically black colleges. There are colleges in the US which originally started at the time of segregation and they were basically only meant for black and colored people who are not being allowed to other universities. Now, of course, many of them are more integrated anyway. But they do get additional affirmative action in the sense they get more funding, a little more funding, to help them come up to speed with research. Now the question is, NSF is very much into making sure that they're spending all this money. They need to know where they're spending this money. And they wanted to answer this very simple question. And they have databases. It took them a whole day to figure this out. Why? Because the information they want is spread over like 8 different databases. And somebody has to actually more or less go through the databases. Okay, the last part of this course, remember I said information retrieval, mining, and integration. The mining part is all this collaborative filtering, classification, etc. Retrieval you already know. I'm unhappy that some of you are already, when you say about this course, you just say in IR course. This is not IR course. IR is just one part of this course. I'm hoping that you'll actually understand other parts too. So the integration part really is to be able to combine structured data of different formats and provide one uniform interface so that a question submitted will be automatically answered even though there are differing schemas. You're integrating information from different places together. That's like a great, a goal worth having. Okay. Now, there are multiple approaches for doing that. If you are coming there from Semantic Web community, one advantage is if these 2 guys write their databases in RDF, they upload their database in RDF, then the integrator needs to map the schemas. Basically, the schema mapping is really relations between attributes. That's what a schema mapping is. It's not the relation between values, it's a relation between attributes. Right? And that can be written in OWL. For a particular subdomain, like you might be able to see these 2 databases, rather than ask both of them to change over to a universal standard, you can let them live their lives and write one OWL description which says this particular attribute is the same as this attribute. this attribute plus this attribute is equal to this other attribute. And if you do that, then you can actually be able to take one query, essentially rewrite it into correct form to both the databases, and send the queries to the databases, collate the answers, and give it back. Okay. From the database community side, this part is considered schema mapping. Okay. Now, if I want to give you the mapping between schemas, I still need a language in which to write this knowledge. And how can we do that? It may be like a sledgehammer, for breaking an egg, but it certainly does do the job. Yes.
This might be a very trivial question, but is this done manually?
Which one? The mapping. Yeah, so the interesting thing in the entire, this is a good setup. It's almost like I paid you 10 cents before coming to class. The entire discussion until now was independent of, in some sense, we didn't take an actual position as to who is writing stuff into RDF, who is writing stuff into OWL. If I didn't say anything, you can assume humans are writing that. Okay, but there is a whole entire issue which is maybe it doesn't really matter as far as these standards are concerned. It doesn't matter who wrote them in that way. If it is written, I can use it. So the next part I'll be talking about is information extraction, where basically these two guys don't actually upload their databases to you at all. They don't give you an API connection to their databases. What they do show you is typically pages. Pages that they think are pleasing to human eyes, and which by definition means are pretty distracting to machines, right? And you need to extract from that page the RDF description first of all. That's information extraction. So if I give you an Amazon page, in fact, when I gave you the Wikipedia table, Wikipedia info box, an extractor essentially had to extract them into RDF triples and then write them down. When it has extracted it, writing it, it was using RDF standard. But the way it got there was by extraction, not by just some human sitting and writing. But both are allowed, essentially. Semantic Web community doesn't, sort of mostly people, they assume that there are enough people who want to write this stuff. Okay? But if there aren't, there is this other way of doing it, which is learn the structure.
So basically, instead of giving the schema, you are actually extracting the structure out of the information that is shown.
I didn't understand your question.
These two things that you have here, these are basically schema, structure of the table.
Yeah.
Instead of directly giving this information extraction, picks it up from the data.
That would be just so. In the case of information extraction, there are two things it has to extract. One is look at an HTML table, HTML page, and realize that it's made up of these tuples. That's first extraction. That's the thing that we'll mostly talk about. The second is to realize background knowledge, saying when somebody says purchase price and somebody else says sale price, they're the same. That's more background knowledge. Learning background knowledge is harder than learning, instance knowledge. Okay? Current information extraction systems at least will get you up to this. Okay? That's a huge area, in terms of, but we don't necessarily know. Basically, both forces are simultaneously in action. There are people interested in extracting knowledge when it is provided in unstructured fashion. That's like improving NLP, at least to a level where reasonable extraction is possible. At the same time, there are people who are essentially writing. There are large amounts of structured data on the web. In fact, there are studies saying that the pages that people read are just a real small fraction of the web. Most of the web is really data from databases. That's just generated on the fly with respect to your answer. You think, Amazon has a whole bunch of, obviously you don't think that Amazon has a whole bunch of web pages sitting there. It generates the web page based on your query. What it has is a structured database. And if you're nice to them, they'll give you API access. If you're not nice to them, they'll give you the page and you need to scrape the screen to get the structure of the table. And once you got the structure, You want to give it to your friend, you need a language in which to give it. And that's RDF. Okay, understood? Okay, so basically that's exactly where we'll go next. So the point I was making in the Ramayana thing in long back, I mean the last class is this is this text, and if you can somehow write this part from this text, you can do better query support. And if you want to extract this structure, you can write it in RDF. Now, I didn't take a stand as to who wrote this stuff.